Hi, my name is Abhijit Day, and I work in the storage engineering team within Veritas. We are going to talk about guaranteed storage quality of service in an upcoming product that we have for OpenStack powered private cloud. The project name is Veritas OpenFlame. We have had few sessions in the last 2 days, and I've invited our distinguished strategist, Doug Snyder from Veritas, to talk about storage quality of service, and our lead engineer, Suhas Dantkale, to talk about the deep dive on the quality of service piece. Okay, so go ahead, Doug.
All right, thank you, Abhijit, appreciate it. So there's a couple of reasons why you want to have true end-to-end storage quality of service, right? The very first thing is what we call VMware packing. Where you place the workload in the most appropriate spot for that workload. That's a difficult decision, right? Because you want to make sure you're not putting it in an area that's already overloaded and can't handle maybe its own workload, plus much less the additional workload you're going to ask on it. Scheduling of other services, if you have busy times, things like that, also needs to be taken into consideration. And we can help Nova with these placement decisions with this upcoming technology. Another big situation is the noisy neighbor problem. This is where you have a very busy virtual machine generating a lot of I/O, generating a lot of traffic that is actually pulling resources away from this machine. Now, we've had this problem since the early days of virtualization. You can remember scheduling mainframes, or at least I can, back in the day, where you had to actually be very careful on how much CPU you were consuming and when you consumed it. And you actually had to sign up for those resources at a specific time because there weren't enough shared resources to go around. Lately, that bottleneck has shifted to storage, but it's still there. Anytime you have a shared resource or contention for those resources, these noisy neighbors can begin to affect the overall performance. And then dynamic load balancing is very critical. When you need to do management operations in OpenStack or really any shared platform, you have to take very careful consideration of when you do a management operation. If you have to migrate a machine or back it up, that generates additional I/O load, which can again impact your applications and application performance. Right? So really, what is end-to-end quality of service as we define it? Well, it's maintaining your application SLAs, for one. That's probably the first and most important measure. A certain number of minimum IOPS for the application to run, perhaps a maximum or a cap, a priority if that workload is extremely important. For example, if your application is up but it's not responding because it's very slow, then as far as the end user is concerned, that application is down, right? So IT may be saying, I'm doing my job, providing a service, but if it's not performing well, the job is not really complete. Effectively utilizing all tiers of storage is also critical. If you have a mix of hard drives and SSDs and perhaps NVMe, it doesn't make sense to place certain workloads on those higher speed, more responsive, but much more expensive tiers of storage. And then storage congestion. This goes back to the noisy neighbor issue. If you have a lot of contention for resources, you have a problem, and you really need to be able to separate that out. And it doesn't mean manual placement. That's just not good enough for today's dynamic workloads. And then you need to resolve a distributed I/O. You know, if you take your IOPS and you spread them across multiple boxes, that does solve some aggregate I/O problems, but it doesn't really solve the scheduling or resource or placement issues. And then you need data management priority. This is really kind of application awareness. How can you guarantee that a certain application gets the IOPS it needs, whereas other applications that aren't as IOPS intensive are okay, right, with either higher latency or lower IOPS. So really, to have an end-to-end solution, you need to tackle all of these issues and probably one or two more that we don't have up here. Now, traditionally, there's been a few approaches brought to bear in quality of service. You can just simply throttle the IOPS, right? Just put a cap, say you can only use so much. And it does solve, in some extent, the noisy neighbor problem, but it really doesn't maximize your utilization. There could be IOPS that could be utilized, but can't because of the cap. It also doesn't do anything to solve the minimum IOPS. If you have an application that has to perform at a certain level consistently, setting a cap doesn't guarantee it's going to get a certain amount of IOPS. The prioritization approach says, well, I have a workload and I know what that workload needs, and I'll guarantee that that workload gets what it needs, but it doesn't really impact the noisy neighbor because another system could then consume and overwhelm that quality of service tag. So that really doesn't help across all applications. Now, tiering has been around for a while, and if you have different classes of disk, well, that works well for some workloads. You can chop up the workload and place certain amounts of your workload on the faster disk, but then your performance is really not that predictable, right? You can't guarantee that when IOPS are needed from a slower class that you really get what you need. So none of these traditional approaches have really solved this problem, which again has gone back really to the mainframe days. This is not anything new as far as what we're solving. But now we're going to solve it with OpenFlame, and I'll turn it over to Suhas, second time, to explain how. All right, thank you.
Thank you, Doug. Thank you, Abhijit. My name is Suhas, and I work in Veritas Engineering. So today I'm going to talk to you about the high level QoS architecture that we have implemented in the project OpenFlame. But before I go into the details, let me also talk to you about some of the QoS feature, the guest to spindle QoS feature that we implemented in the Cinder. We had a couple of sessions day before yesterday and today where we talked about some of these features in detail. So let me try to just reiterate some of these features. So basically, what we needed to do was we needed to bring the DAS awareness in the Cinder. So direct attached storage awareness into the Cinder, and then we also need the adaptive features and the feedback mechanism implemented in the Cinder, and also some of the scheduling filters for VM placement and the storage and VM affinity to be maintained. So this is the optimal QoS architecture that we have implemented in OpenFlame at the high level. So as you see in the diagram, there are two levels we are doing the QoS. The top layer is the near guest layer. It's near the guest component, and the bottom layer is near the storage component. So near storage component is per tier specific. So as you see in this example, for SSD, we have one instance of the near storage QoS, and for SSD there is another. So near guest component, what it does is it tries to understand the SLAs, QoS SLAs set by the application, set by the user for a certain application, and it tries to distribute the credit, IO credit, and does the flow control, and is typically implemented in hypervisor, which is the top most layer in the IO stack. And the near storage layer is it's again per tier, like I talked about. So it's implemented at the bottom most layer in the IO stack, and it understands the physical storage media, and it controls the storage congestion, and it communicates it back to the top layer, near guest layer, and it's in a constant feedback loop with the top layer, so that the top layer can take the better IO credit distribution decisions. Doug talked about some of the problems that traditional QoS techniques doesn't solve, even if they combine together. So essentially what we are trying to say here is unless you know the storage characteristic of your underlying storage devices, and unless you are in a constant feedback loop with the upper layer, we cannot really implement what we mean by end-to-end QoS. So with that, let me go to the demo very quickly. So what we are essentially showing here is we have 5 VMs created here, all with different flavors, and all have different storage QoS characteristic set, and like min IOPS, max IOPS. And we are trying to demonstrate that a noisy neighbor will not consume all the IOPS, and will make sure that the IO credits will be given to the other non-noisy, well-behaved workloads. So here you can see that so IOPS are throttled. So the IOPS are throttled at the max level, whatever is set. And also at the same time we also make sure that minimum IOPS of all these VMs are met. Because that is very important. So we make sure that the application IOPS are throttled at the max level. At the same time, the minimum IOPS are guaranteed for all of the VMs. And let me take you through some of the graphs that showcase the QoS we have implemented. So on the left-hand side, you can see that without QoS enabled, and on the right side, we can see the graph when the QoS is enabled. The red line which you see on the left side is actually the noisy neighbor. It's doing a lot of IOs and thereby overwhelming the underlying storage. And you can see that there is sudden drop in the IOPS because at the point where the IOPS are dropped, the storage is congested. So we cannot do, whatever we can do at the application layer, any throttling, that will not help because your underlying storage itself is bottlenecked. And it's also not guaranteeing the IOPS, minimum IOPS of the other VMs running, like green and yellow and blue. On the right-hand side of the picture, you can see that with the QoS enabled, though noisy neighbor is doing a lot of IOs, it's not impacting the IOPS of the other VMs. The blue one is getting its minimum IOPS, and yellow and green are getting their minimum. So this is the throughput SLA guarantees given by the OpenFlame QoS. And then we have the improved latency with end-to-end QoS. So we are not only adhering to the latency set by the user, but we also make sure that the latencies are improved because we are utilizing the storage in a better way, and we are making sure that the storage is not congested. So on the left-hand side, you see that without QoS enabled, you can see the latencies are going up till 8 to 9 millisecond in this set of experiments. And also on the right-hand side, you can see that the latencies are capped at 2 to 2.5 milliseconds. Even the noisy neighbor is also getting, is getting 2.5 millisecond latencies. And with that, let me hand over to Abhijit for the further discussion.
Thanks. Thanks, Suhas. So, thanks for explaining Doug for explaining the quality of service for storage, and Suhas for explaining a quick deep dive into the implementation that we have in our product, which we are launching later this year. It's called Veritas OpenFlame. Is a software-defined storage solution for OpenStack powered private cloud. We talked over earlier session in talking about Ceilometer and how we leverage the storage insights. Yesterday we talked about Cinder, the dash-aware Cinder, how we can achieve enterprise-grade storage, scalability and performance for OpenStack. We just covered predictable guest-to-spindle quality of service for OpenStack. In our upcoming session at 4:15 in this room, we'll cover live migration for OpenStack Cloud. These are the 5 sessions we have in this summit. You can also visit our booth in the marketplace rest of the day in C29 to learn more about Veritas OpenFlame. Thank you so much from all of us, Doug, Suhas, and myself from Veritas.